Okay, so for the last two questions or examples in this set of notes for section 4.1, what I basically want to do is kind of impress upon you the importance of really checking and making sure that EVT applies or doesn't apply, because we're going to look at what happens if EVT fails and some of the techniques that are going to be coming in the rest of Chapter 4. What I do want to stress, though, is if you do have a continuous function on a closed interval, then extreme value theorem is going to be the easiest way to determine where you have your global maxes and your global mins. If you are trying to determine your global extrema, and again, I probably want to go ahead and put this on here, that we're really talking about the global extrema, and also sometimes the local extrema. We can determine where those are, but there's no interval given, which would mean that EVT doesn't apply, or we don't have a graph, or we don't have continuity in the problem. And so we're going to look at two examples. Each one kind of has different characteristics of why EVT fails. So if you take a look here at example 12, let's first start by finding our domain. Our domain here, we have a fraction, so we have a division by zero problem, and we have an even radical, so we can't take the even radical of a negative number. So we know that in finding the domain, 4 minus x squared has to be greater than 0 in order for this to be defined. So to determine when that is, we will use our handy little sign chart. We'll do our factors, 2 plus x, 2 minus x. Your expression 4 minus x squared is going to be 0 at negative 2 and 2. So 0 and 0. So we know that those are not going to be included in the domain because we have a division by zero problem there. We test values in between to determine when the expression is positive or negative, or we simply go, it's a parabola that opens downward, so it would be negative plus negative going across here. So the only time for which this expression is going to be defined is going to be in between negative 2 and 2, so negative 2 to 2. So as soon as we take a look at that, even though they didn't give me an interval, I did find an interval for which this function is defined. However, the problem is it is not closed. So EVT fails because there's no closed interval. And so what are we going to do if we are trying to find extrema and wanted to work with this function and determine what's going on? Well, there's a couple of things that we're going to do. We are going to use the derivative because those critical points are going to be important. We're going to kind of sketch the graph, and we're going to analyze the graph and use all the calculus that we've learned so far to help analyze what's going on in the graph. Now, the first thing is that because we have a undefined values here before negative 2 and 2, and we're not defined, we have discontinuities at negative 2 and 2, one of the questions we might ask is what kind of discontinuity do we have at negative 2 and 2? Now, obviously, we can't do the limit as x approaches negative 2 from the left side because there's no graph over there, but we can certainly take a look at the limit as x approaches negative 2 from the right side of f of x and determine what's going on here. And when you take a look at this, remember that when we're doing this limit, if I were to test this by doing my direct substitution, I would end up with a number 1 divided by 0. And remember that that's a characteristic that we have a vertical asymptote. And so really all we need to do is determine whether it's going to infinity or negative infinity because we have a vertical asymptote there. And this is always positive, and so really we just have to check at values close to negative 2 what's happening. Well, we already determined that it's positive there, so this must be heading to positive infinity. So there must be a vertical asymptote at x equal to negative 2, okay, and we're heading up to infinity, approaching it. And then likewise, for the same reasoning, we're going to take the limit as x approaches positive 2, but from the left, because that's the only place where it's defined. And again, for the same reasoning, since when we plug in our 2, we would get a number divided by 0, then that's an indication that we have a non-removable discontinuity, a vertical asymptote, and it's going to be positive on that, close to 2 on that side, so we must be going up to infinity. So both limits did not exist because we had vertical asymptotes, but we can easily see that we're heading up to infinity. So we can actually kind of start sketching the graph over here to kind of give ourselves an idea of what's going on. Make that a little bit more straight. All right, so right now at 2 and -2, we're going to put vertical asymptotes. I'm going to use the line drawing tool to make it a little easier on myself. So vertical asymptote at -2 and a vertical asymptote at 2. And we pretty much have determined the behavior of the graph that as I head close to this asymptote, it's going to be heading up and up. So immediately we can have an idea that there may be some extrema that are going to fall down here somewhere between -2 and -2. So since I believe that there may be extrema here, let's go ahead and determine our critical points by finding our first derivative. So we'll find f prime of x. Maybe before I find f prime of x, maybe we want to rewrite f of x into a nicer form to take the derivative. So I don't have to use quotient rule. I'm going to write it as 4 minus x squared to the -1/2. So that way I can use chain rule to find my derivative. So f prime of x, -1/2, 4 minus x squared, subtract 1, -3/2, times chain rule, derivative of the inside, -2x. And then let's rewrite that into a nicer form. Okay, remember we've been practicing all along this. Once we get the derivative, let's simplify it into its nicest form. Our 2's are going to cancel. That's going to go away. The negatives are going to cancel. So those are going to go away. So we pretty much are going to end up with, in the top, we're going to have x, and then in the bottom, we're going to have the square root of 4 minus x squared, and that's all cubed. And so if we take a look at our domain of our derivative, again, tying this all together, what we'll see here is that the domain here is the same as the domain up there, that it's going to be -2 to 2. And so it's going to be differentiable for all the values in the domain of the original one, that every point in between -2 and 2 is going to have a slope of a tangent line that exists. Let's determine, so f prime of x does not exist for x not in the interval -2 to 2. Right? And we don't have to worry about any of those. They're not going to give us any extrema because there basically is no graph there, and we've already determined that we have asymptotes. So now to find our other critical points, we're going to set the derivative equal to 0, which is why we put it in this fraction form, which happens when x is equal to 0. And so that is going to be where we're going to have an absolute max and min. Now, but that's not enough. I might go ahead, since this is a critical point, calculate f of 0, just to figure out where it is in the graph. If I plug in 0, I get 1 over the square root of 4, or 1/2. So here's my 1, 2. So we're down here at that. Now, more than likely at this point, you're going to be like, hey, this is going to be a global minimum on this graph. What we've learned some things about this graph. What I want to do is I'm going to do a sign chart for the derivative, because I want to determine where does f of x increase or decrease. Right? So that's a question. Remember, we're previewing things that are going to come in the rest of chapter 4. And so what this does is this is going to give us, this is what we call the first derivative test. The first derivative is going to tell us whether it's positive or negative, is going to tell us where the original function increases or decreases. So our critical values, we already know that it's not defined, okay, for -2 and 2, and neither was the derivative. So we're just going to do undefined here, undefined here, undefined here. I'm going to put a U here, and down here I like to say what's happening. We already know that this is a vertical asymptote, so I'll put that in. So now what we want to do is we want to figure out what's happening on the derivative in between -2 and 2, and we have to add the critical point of 0, because that's where our derivative was 0, which is going to mean that it's a candidate for an extrema. So we check before and after 0 on the derivative. If I were to plug in, say, -1 into the derivative, f prime of -1, and we really just need to figure out whether it's positive or negative. You would have a negative over a square root, which is always positive, so this would be less than 0, so I'll put a negative there. F prime of 1, using that as my test value, 1 over a positive number is going to be positive, so now this is positive. And what this tells me about f of x is that when the derivative is negative, f of x is decreasing, and when the derivative is positive, f of x is increasing. And so that's the information that we needed in order to prove that we actually have a minimum at x equal to 0. So because f prime of x equals 0 and f prime of x switches from negative to positive, we now know that there is a local min at x equal to 0. Okay. Now the next question is that's what the derivative equaling 0 at an x value and then switching signs from negative to positive gives us that there's a local min. Now to go even farther and to get it to be a global min, what we would need to know is that since for all x in the domain -2 to 2, before 0, let's make it x equal to 0 so we're clear. Before x equal to 0, f prime of x is less than 0, and after x equal to 0, f prime of x is greater than 0, then x equal to 0 is a global min as well. So not only does the derivative switch, we know that for the entire domain, from where you start, that it is the derivative is negative before 0, which means f of x is decreasing, and then after 0 for the rest of the domain, the derivative is positive, which means f of x is now increasing. That has to be the only location of where you have the lowest value. So we pretty much can come back up here and sketch in. If we wanted to get a couple more points, that's fine, but we can have this idea, and now we've proven using calculus that we have a global min. So there is a global min value of 1/2 at x equal to 0 on f of x. And that's what we were able to prove. Now, this gives us a lot of information, kind of idea of previewing of coming attractions. This part right here is what we call the first derivative test. The first derivative, when you do a sign chart, tests to determine where a function is increasing and decreasing, and the first derivative test is going to tell us where we have local extrema. And then in order to get the actual, and there's two key parts to this first derivative test. You have your derivative either is undefined or equal to 0, so that's this critical point. And then you have to show that the derivative switches from negative to positive, and that's what's getting it to be the min part. Once we know there's a critical point, you know that it's a candidate for extrema, and then you prove that it's either a local min or a local max by looking at what it's switching from positive to negative or negative to positive. And then the second part of it, to get that you have a global minimum, this is what we call the modified first derivative test. And what that does is that's going to allow us to determine that that local min is actually a global extrema on the graph as well. That you have to examine the entire domain and see what happens for the entire graph before and the entire graph after it. Now there's some more things to come. We're also going to have a second derivative test, and we're going to have a modified second derivative test. I'll go ahead and preview that here as well, trying to keeping this idea of these are things that are going to come. Now obviously you can see based on the work that I'm doing so far in order to just prove this that EVT for global maxes and mins is going to be the easiest and the fastest, but you have to have a continuous function and a closed interval to take a look at it. Here I unfortunately did not have a closed interval even though it was continuous on the open interval -2 to 2. Let's do the second derivative test and just kind of preview what that's going to give us coming down the pike in chapter 4. So the second derivative test. Now, since the second derivative is the derivative of the first derivative, it tells us whether your first derivative is increasing or decreasing, which has to do with whether your rate of change is increasing or decreasing, which actually has to do with concavity. So what we're doing here in this, we would start out the second derivative test pretty much the same as the first derivative test. You would determine that your f prime of x equals 0 and you would get your critical values, and we would still have the -2, 0, and -2. Now let's go ahead and find the second derivative just to use that and show how this works. So we had x, and I'm going to rewrite this again back into x times my 4 minus x squared to the -3/2. And so, whoops, and that's your first derivative. And I'm going to use that in that nicer form to take its derivative. We're going to have to use a product rule to find the second derivative. So I'm going to do x times the derivative of the second one. So that would be times -3/2. 4 minus x squared, subtract 1, -5/2, times the derivative of the inside, -2x, plus, and then I need the derivative of, well, we'll do the 4 minus x squared to the -3/2 times the derivative of x, which is 1. Now when you get to here, this is where you're going to work on your simplifying skills. I'm going to look for, well, first off, things that cancel. So this 2, this negative, and that 2 is going to go away. I look for common factors, and I do have a common factor of 4 minus x squared. The smaller power is -5/2, so we're going to pull that out. In this term, you're going to be left with an x, a 3. This is pulled out, and an x, so we have 3x squared plus, and remember when you are factoring, you're dividing, and so you're subtracting your exponents, -3/2 minus -5/2, -3/2 plus 5/2 would give me 4 minus x squared to the 2/2, which is 1. And so I'm going to omit the parentheses because they're not necessary. And so now in its nice simplified form, we're going to end up with in the top 2x squared plus 4 over the square root of 4 minus x squared to the 5th. Okay, so now, of course, looking at the bottom again, we see that the domain of the second derivative is -2 to 2, just like we've had all along here. So we know that it was not, if it's not differentiable for values not between -2 and 2, it's not going to be, the second derivative isn't going to exist either, and we see that. And we also don't have any new discontinuities on this one, so there's no other places where maybe the derivative itself had a cusp or was discontinuous. Now all we need to do is determine critical values for this one. So we get f double prime of x equal to 0, and that's going to equal 0 when 2x squared plus 4 equals 0, but hopefully you recognize that if I subtract 4 and divide by 2, this is for no values. Okay, so there is no place where concavity is going to switch on this. This is what we call a possible POI. That's what this is going to be finding. We don't call these critical points anymore. We call these possible points of inflection. because this is going to tell us where the first derivative is going to switch from increasing to decreasing, which is telling me where concavity on the original function is switching from concave up to concave down. So that's a possible point of inflection. So we have no points of inflection. And so basically, if we want to prove that at x equal to 0, that is a local min, and the reason that we can do that using the second derivative is because the second derivative at 0, you have positive over positive, is greater than 0. So f of x is concave up at x equal to 0. And that is what's going to give us that it is a local min. And that is what we have as our second derivative test. So the second derivative test for Extrema is that we take the critical point from the first derivative where you were switching your signs, okay? And you haven't possibly done this. I mean, you have an option. You either do the first derivative or you do the second derivative test. So you do the first derivative and you determine your critical points. And then you look at your second derivative and you plug it in, and if it is a positive second derivative, the graph is concave up, which would mean local min, and if your second derivative is negative, that would mean the original is concave down, which would make it a local max. Now again, this only gets you the local value. It doesn't get you that it's a global value. The modified second derivative test, again previewing all these things that are going to come, the modified second derivative test is looking at the entire domain. Since f prime of x is greater than 0 for all x in -2 to 2, then f of x is concave up for all x in the interval -2 to 2. So f of x, or let's do at x equal to 0. So x equal to 0 is also a global min. Right? That we have to show that it is concave up for the entire time. If it had switched, if it was concave up and then concave down, we wouldn't be able to get that that's a global min because there may be a point lower because of the switch in concavity. So that's a good preview. This is just kind of an example of showing you all the things that we're going to be able to do using calculus to analyze a graph or a function that we don't know the graph of. We can use limits to determine our behavior, getting close to discontinuities, so we can determine the type of discontinuities. We can use the first derivative to get critical points for local extrema, and then we can use those critical points by creating a sign chart and determining what's happening on our function. And then even though I didn't really write the sign chart for this, you technically are doing a sign chart for the second derivative when you do the second derivative test, because the second derivative, just like the first, we would have our undefined in these locations. We had positive here, so what that tells us about the original function f of x, it was also undefined here. We already determined vertical asymptote here and there, and then undefined here, that in between it's going to be concave up. And so this idea, and then since x equal to 0 fell in between here and was positive, that because it was a critical point back here was going to be a local min. All right, so that's kind of a preview of coming attractions from that one. The next one that I want to look at, example B here, what that one does is we have a piecewise function. And so we want to sketch the graph and we want to kind of see what's going on with this. Now, the two things that we're going to review here is, remember that to find our critical points for extrema, we need to determine where f prime of x equals 0 or the f prime of x does not exist. Now, to start out with the f prime of x, when you start to go to find this, because this is piecewise, well, certainly we can take the derivative of each piece. So the derivative of 5 minus 2x squared is going to be negative 4x. The derivative of x plus 2 is going to be 1. However, to start out, I only get x less than 1 and x greater than 1. Because remember, we have to do a little work in order to determine, is f of x differentiable at x equal to 1? Does it exist? And remember, the idea is we need to make sure that it's continuous at x equal to 1. All right, so 1, we want to show f of x is continuous at x equal to 1. And then we want to show, 2, that f of x, f prime of x exists at x equal to 1. So we have to first meet the hurdle of continuity, and then we want to meet the hurdle of showing that the derivative exists. Now, if I was trying to determine if EVT applies, really where I have a problem here is, well, first let's do the continuity, just to see what's going on. Now, clearly we have a continuous function here, a continuous function here. The only place where it might not be continuous is at x equal to 1. So let's do our continuity. So f of x continuous at x equal to 1. Does f of 1 exist? And the answer is yes, because I have an equals right here. F of 1 equals, plug in your 1, and you're going to get 5 minus 2 or 3. And then we're going to check the limit as x approaches 1. We're going to do from the left of f of x. That's going to be the limit as x approaches 1 from the left is the piece 5 minus 2x squared, which is going to be 3 by direct substitution. And then we check the limit as x approaches 1 from the right of f of x, which is the limit as x approaches 1 from the right of the other piece, x plus 2, which is also 3. Those are the same, so the limit as x approaches 1 of f of x exists. Check. So this was number 1 in our definition, number 2 in our definition. And then number 3 in our definition is that the limit as x approaches 1 of f of x was the same as f of 1, which was 3. So f of x is continuous everywhere, since it's continuous at x equal to 1, and each piece is polynomial. Alright, so we have continuity met. And then you might wonder, well, why can't I use EVT? I have continuity. The problem is that then we take a look, we weren't given a closed interval. So the domain of this, the domain of f of x, is two pieces that are polynomial, and then x less than or equal to 1, x greater than 1, you put these two together, your domain is negative infinity to infinity. So clearly we have a continuous function that's continuous everywhere. And so therefore we are going to have this idea that, sure, we can't use EVT because we don't have a closed interval. So EVT fails. All right, so now we're going on, we're going to find our critical point. So that was all just determining our continuity. So now we're going to go to our derivative, and the next question is, I really need to know, is it differentiable at 1? Because I'm going to set the derivative equal to 0. Okay, critical points, f prime of x equals 0, or f prime of x does not exist. So I need to do differentiability. Well, we already know that it's differentiable everywhere on the left side and everywhere on the right side of 1. So the only place to check where it's not differentiable is going to be at 1. And so on that one, if you'll recall, to show that the derivative exists at 1 when you have a piecewise function, is we need to show that the derivative is smooth, that it itself is continuous and does not have a jump when you're coming into your x equal to 1 point. So we're going to show that the limit, okay, so at x equal to 1, we want to show that the limit as x approaches 1 of the derivative exists. And if that does exist, then we know it's differentiable at 1, and that would not be a critical point for an extrema. However, if we take a look at this, let's do our left and our right. The limit as x approaches 1 of the derivative, let's do it from the left, would be our left derivative, which was minus 4x. So we have the limit as x approaches 1 from the left of minus 4x, which is going to be negative 4. I check the derivative on the right. The limit as x approaches 1 from the right on the derivative is the limit as x approaches 1 from the right of the other piece, which was 1. And the limit of a constant is a constant. So we have left and right limit on the derivative are not the same, so it's not smooth. So f of x is not smooth, and because we have derivative slopes that are existing but not the same, we're going to conclude that there's a cusp at that location. Okay? All right, so that's that. And then let's take a look at our critical points where the derivative is equal to 0. Is there a place where the derivative is equal to 0? Because maybe that's a candidate for an extrema. Right now we have at x equal to 1, there may be an extrema. We know that there's a cusp there, and the question is going to be whether the cusp comes in and then keeps going. So you see how you can have a cusp but it's not an actual extrema because we're increasing the whole time? Or do we have a cusp that's doing something like this where that might be a possible extrema? So we're going to look at that situation, and we're going to start fleshing out the graph here on this to see what's going on. We definitely, since that's a critical point, I might want to go ahead and find f of 1, which I already did, which is 3. So we're going to use this information in a second to determine what kind of local extrema may be there and if there is one there. All right, so now let's take a look over here at where the derivative is equal to 0. So now when you have a piecewise function, you really do have to look at both pieces. So I'm coming back up. On the derivative, you're going to have to set the first piece equal to 0 and the second piece equal to 0, and make sure that the value where it is 0 is in the domain given for that piece. So we're going to do our negative 4x equals 0 when x equals to 0. We're going to check the domain for that piece, which was x less than 1. 0 is less than 1, so yes, and so this is going to be a critical point. And then the other piece, 1 equals 0, well that's never, so we don't get any critical points from that. So what we have right now, if I start to make this sign chart, we have two critical points. We have a critical point at 1, and we have a critical point at 0. And we're going to put our derivative on here, f prime of x. We're going to put f of x on here, and we're going to talk about what we know about this function. All right, we know that the derivative was 0 here, and it was undefined here. But f of x was defined here. It had a value. It was 3. So we know that, let's check our derivatives, what's happening. We did the before and the after, and I already did this work, that if I'm on the left side, the slope is negative. If I'm on the right side, the slope is positive. And so what that is telling me here, and then we went to different values here, that there must be a cusp located at that location. Now f of x is decreasing and then increasing. Now I also need to test down here just to make sure, since we have a 0 here, if I pick a value like negative 1 and I plug that in the derivative, negative 1 is going to be a positive value. Right? So we have a positive value. So f of x must be increasing, then I have 0, and then decreasing. This must be the location of a local max. Okay. So kind of putting your reasoning, and this is also one of the things to talk about. Sign charts they don't look at sign charts for your information. You have to write the words that go to explain the sign chart. All right, so we would say because f prime of x equals 0 and f prime of x switches from positive to negative, then at x equal to 0, there is a local max. Okay, now we're going to go to this part now at x equal to 1, because at x equal to 1, f prime of x does not exist, but f of 1 equal to 3 existed, and the slopes, the limit as x approaches 1 from the left of f of x did not equal, or the derivative, f prime of x, did not equal the limit as x approaches 1 from the right of f prime of x. There is a cusp at x equal to 1. And since the derivative switched from negative to positive, x equal to 1 is a local min. All right, so now let's take a look at our graph. We've learned a lot about this, and these are fairly easy for us to graph too, because it's just a parabola and a line. We know that f of 1, which is where we had a critical point, is going to be 3. 1, 2, 3. So I'll add that point in. We also had a critical point at x equal to 0, and f of 0 would be 5, so let's put that in. F of 0, 3, 4, 5 would be 5. While I'm thinking about this, let's do our intercepts for our parabola, because it's always important to figure out if you're graphing where the graph crosses the x-axis. F of x equals 0. On this we would have 5 minus 2x squared equal to 0, 2x squared equals 5, x squared equals 5 halves, x equals plus or minus the square root of 5 halves. So square root of 2.5, bigger than 1, smaller than 2, so 1 point something, plus or minus 1 point something. Now down here, I'm not going to worry about the one that would have been here, over here. So somewhere, we'll just guesstimate. Our vertex of our parabola, let's look at all this pre-calculus we're bringing in here. Our vertex is going to be halfway in between these two, and since it's symmetric, it's going to be at x equal to 0. So the vertex is going to be 0, 5. So we already have that in. That's nice. And then by symmetry, since that was 3, there must be a 3 right there. So our graph, the left piece is a parabola, and then the right piece has a slope of, sorry, I have to keep coming back up, 1. And so we're going to go up 1 over 1, and that's going to be good enough to go in here. So this is a picture of f of x. Now, as we can see here, that if we're thinking about what's going on with this graph, we are increasing, decreasing, and then increasing. We know that the limit as x goes to infinity of f of x equals infinity, and we also know that the limit as x goes to negative infinity of f of x equals negative infinity. And basically, knowing that piece of information, I know that there are no global extrema on the graph, because there's no lowest y value, or no highest y value, so there's no global extrema. And so this is kind of giving you a preview of kind of a little bit of everything that we're going to look at in the remaining parts of Chapter 4. We've seen some preview of the first and second derivative tests, or the modified ones. You'll notice that I'm using my information from pre-calculus to find intercepts and domain. and vertices of parabolas, that I'm using the limits that we learned in Chapter 2 to determine behavior, to determine types of discontinuities, and then to determine end behavior so that I can see that I have no global extrema. So what we're trying to do here in Chapter 4 is really it's all about sketching graphs and determining the behavior of f of x in order to find things like extremas and points of inflection and the behavior of the graph near discontinuities and on the end. So we're kind of putting everything together here and using calculus in order to help us out. All right, so that was a preview of coming attractions, and we'll be working on each of these little parts individually and practicing in the remaining sections of Chapter 4.